particularly zero in on what's known as ordinary annuities. Again, as we said in the previous videos, we're going to be looking at how to use the tables. The tables are based on formulas, and choosing the correct table is key to solving the time value problems. There are two types of problems: the single sum problems, which were addressed in the previous video, and annuity problems, which we're going to take a look at now. Single sum problems involve a single value at the present, which grows to a single value in the future. Now we're going to take a look at annuity problems, which involve a series of payments. Either we're getting a series of things we're receiving or a series of things we're paying. In this case, example here, we deposit $1,000 every year for 3 years. So we have this series of deposits, as opposed to the example of the single sum where we deposit $1,000 today and we walk away and we leave it, and then we come back in 3 years. Here we're depositing $1,000 every year. Now, to be an annuity, it has to have that series of payments, okay? But it also requires 3 different things. Periodic payments or receipts, this is the series, okay? And we call those payments rents. You don't necessarily just mean rent like renting an apartment, but that's the word that we use, okay? And this amount, it has to be the same amount, is paid every period. So if I were to deposit $1,000 this year and then skip a year and then another $1,000 for the next couple years, well, that wasn't an exact series because it has to be the same amount every period. So because I skipped that 1 year in the example I just gave, it would not be an annuity problem that we could solve easily with one table. Okay. The same length interval needs to be between each payment. So here we had the $1,000 deposited every year, okay? So that doesn't mean that sometimes it's 8 months and sometimes it's 14 months. We're talking about a 12-month, once a year period. It's the same period between each payment. And we have to have the compounding has to be once each period. So if I'm making a deposit once a year, but compounding is happening twice a year, then that won't work with these tables, okay? The compounding would also have to be annually for us to be able to easily use the tables. Does not mean if any of these rules are broken that we can't calculate out the answer, but it will be more complex, and we will have to break the problem down into pieces and then add the various pieces together. There are 2 types of annuities. There's an ordinary annuity, means that the rents or payments or receipts occur at the end of each period. So at the end of each year, we're going to deposit the $1,000. Annuity due means the rents or payments or receipts occur at the beginning of each period. So we're going to deposit the $1,000 at the beginning of each year. Okay, and so the difference becomes in how the interest is handled. If it's an annuity due, we're going to have extra interest because it's at the beginning of each period. So that's one extra interest that's going to be added in there. So when we're looking at a time value problem, we first have to decide if it's a single sum or an annuity problem. And then secondly, we have to see if we decide it's an annuity, we have to look and see Is it an ordinary annuity or an annuity due? Okay, now we had 4 variables that we looked at for the single sum problems, and we have 4 variables here. And just like them, if we solve 3 of these variables, then we can solve the 4th. Okay, so, but the 4 variables are slightly different than the variables for the single sum problems. We still need the rate of interest and the number of time periods. That's the same. But here we need the future value or the present value. Whereas with single sum, we needed them both. So here it's one or the other. One problem might involve present value. The next problem might involve future value. We have to know which one. And then finally, the amount of the rents, those are the payments or the deposits or the receipts that we're getting every period. Okay, how much are those? Okay, so these are the 4 things that we need. Here's our timeline. Across the bottom, we have a present value and a future value, but we're only going to use one of those. We have the interest and the number of periods. And then each line, where the 1, the 2, the 3, the 4, and the 5 is, represents a period and how much is the rent at each one of those periods. So again, if it's an ordinary annuity, the rents occur at the end of each period. There's no interest during the first period because you can see from 0, which is today, up until the end of period 1, there's nothing in there. Okay, so the first rent doesn't happen till the end of the period, and so this whole first interest is not there. Okay, if you have or need the future value, then present value is not part of the problem. So in this case, in this timeline you see here, the future value is what we need. The rents are the $20,000 a piece, and we would have to put the interest and the number of periods. Obviously, in this case, 8 periods, and the rents are happening at the end of each of the 8 periods. Okay, and we do not have a present value. We don't talk about it. We don't need it. We don't have it in our formula. Now this shows you how an annuity could work if you wanted to do it as separate single sum problems. Here is where we're depositing $1 at the end of each of 5 years. Earns 12% interest, and each one of these, so at the end of the first year, we deposit $1. Okay, how much do we have at the end of 5 years? Well, we can do that as a single sum problem, and we would end up with $1.57 roughly. The end of the second year, we deposit $1. How much do I have at the end of 5 years? Okay, which is basically 1, 2, 3 periods, okay? So, or 4 periods actually, and we would have $1.40. So each one of these is treated as a separate single sum problem. Now the $1 at the end of the 5th period is only worth $1. There's no interest is added on to that at all. Okay, so we have 5 separate dollars. We can calculate each separate one using a single sum formula and then add them all together, and we would get $6.35 roughly. Okay, but there's a much easier way to do that, okay, where we can just do it in one calculation rather than 5 calculations and then add them together. Okay, and we're going to be using table 2. here's our formula. We want to know future value, okay? And so we're going to say future value equals R, that's the rents, times table 2. So here is an example. What's the future value of five $5,000 deposits made at the end of each of the next 5 years, earning interest of 12%? Okay, so we're making our timeline. Okay, in this case, we want to know the future value. So future value is a question mark. Present value is just ignored. Okay, our rents are 5,000, so each period is 5,000, and they're at the end of each period. So this is an ordinary annuity. Our I is 12%. Our N is 5 years. Okay, what table are we going to use? Well, we need the future value of an ordinary annuity, so that's going to be table 2. Okay, we're going to use the formula that the future value equals R times table 2. Okay, so here we're in table 2. Go down the 12% interest, and across the 5-year period, we get 6.35285. We multiply that times the rents, and that gives us the future value of $31,764. Here's another example. Gomez Inc. will deposit $30,000 in a 12% fund at the end of each year for 8 years, beginning December 31st, 2020. What amount will be in the fund immediately after the last deposit? Okay, so once again, they want to know how much will there be in the future. So our future values are question mark. Our rents are $30,000 each period. We have 8 periods, and we have interest at 12%. So we're going to use the formula FV equals R, rents, times table 2. So here is our table 2. Our interest is 12%. So we're going to go down that column to the 8 years across. That's 12.29969. Our formula is that we're going to multiply the rents times that factor. And so 30,000 times that factor is our future value of $368,991. Okay, now what if we want to know how much are going to be the rents? Okay, so assume that you plan to accumulate $14,000 for a down payment on a condo 5 years from now. For the next 5 years, you earn an annual return of 8%, compounded semi-annually. That's twice a year. How much should you deposit at the end of each 6-month period? We know the FV, which is 14,000. Okay, we know the rents are at the end of the period, so we need FV of an ordinary annuity. That's going to be table 2. Okay, our I is going to be 4%. How did we get that? We took the interest of 8% divided by 2 because we're compounding twice a year. And we took the number of years, 5 years, and we multiplied by 2. So our N is 10. So we're going to see FV equals R times table 2. And for our table, we're going to look up 4% interest, 10 periods. Okay, so here we are here in table 2, and we have 4%, so we're going to go down the 4% column, and we have 10 periods. So where they come together is 12.00611. Okay, and so we have FV equals R times 12.00611. Now I'm going to need to divide each side of that equation by the 12.00611. Okay, and so that will give me the 14,000 FV divided by 12.0061 equals the R. Okay, so once I do that, that's going to be 1166.07. So that becomes my R. You can always double check that. You can see if 1166.07 times the factor 12.00611 equals the 14,000. Here's another example. Okay, how about if we want to calculate out the number of periods? Suppose that a company's goal is to accumulate 117,332 by making periodic deposits of 20,000 at the end of each year, which will earn 8% compounded annually while accumulating. Okay, so here they show you the formula, but you could also take a look at the way we do it, which would be we have the future value. Here's our timeline. Our future value is 117,332. It's compounded annually, so our interest is 8%. Our rents are 20,000 per period, and our N is what is unknown, the question mark. So we're going to use, we have or need the FV, so we're going to use FV equals R times table 2. So we're going to fill in the numbers we know. FV is 117,332 equals R, 20,000 times table 2. We need to divide each side of the equation by the 20,000 to get rid of it so that table 2 is by itself. Okay, so 117,332 divided by 20,000 ends up equaling table 2. That's going to equal this 58666, and we're going to look down the 8%. Okay, here's it looks like a little typo. It's got 0.58666. It should be 5.8666. Okay, and we're going to look down the 8% column until we get to this 5.8666, and then we'll go across and see how many years. So here is our table. We're going to go down the 8% till we get to the 5.866. Now we'll come across to see how many periods is that. That is 5 periods. We can double check that. The 20,000 times the 5.866, does that equal the future value of 117,332? Yes, it does. So the answer is 5 years. Okay, so that was all discussing the future value of an ordinary annuity. Now we're going to turn our attention to the present value of an ordinary annuity. Okay, and that's where we either have or need the present value of a series of equal amounts. Okay, and the periodic rents occur at the end of each period still. Okay, so here we have or need the present value when we don't use an FV in the problem. What are we going to do for that? That is table 4. The present value of an ordinary annuity is table 4. Okay, we're still going to make a timeline, put in our known values, put in the question mark for the unknown value. Here is an example. Jamie Ewan wins $2 million in the state lottery. She will be paid $100,000 at the end of each year for the next 20 years. So I take $100,000 times 20 years, that'll give me the $2 million. Okay, how much has she actually won as far as what is the present value today? Okay, assume an interest rate of 8%. Okay, So here's the 100,000 that she's going to get every year for the next 20 years. But the 100,000 that she gets 20 years from now is not worth today what the 100,000 that she's going to get 1 year from now is. Okay, and so we want to know what is the total of all these 100,000s is, what is the total of it worth today? If they handed us one lump sum, how much would it be? Okay, so in this case, we need the present value. It's an ordinary annuity, meaning it's coming at the end of each period. So we need table 4, and our formula is PV equals R times table 4. So in this case, our PV is the question, equals R, which is 100,000, times table 4. Okay, this is once a year, so we'll use the 8% and 20 years. So here is table 4, and we have 8%. We go down to the 20 years, and that's the 9.81815 is the factor. So we have PV equals R times table 4. So the R is 100,000 times table 4, 9.81815 equals the present value that we're looking for. So if we divvy out the $2 million by handing her 100,000 each year, what that's worth today is 981,815. So her 2 million is worth less than 1 million. Okay, and taxes will take half of that. Okay, so if the state will sometimes give you the option, well, you can take a lump sum today, or you can take the 100,000 each year for 20 years. So if we took the lump sum today, and if what the state said was, oh, we'll give you $1 million today, well, that's more than the present value, so that would be worth saying yes to. If they say we'll give you 900,000 today, then that's actually worth less than what the 100,000 for 20 years is. So you would have to try to make up your mind at that point. Okay, here, what if we need to calculate the interest rate? Okay, so you have a MasterCard balance due of $528.77. You can pay it off in 12 equal monthly payments of $50 each. So that's our rent, our equal payment, $50, okay? And that's 12 period, okay? It doesn't matter if the period's a month or a year, 12 periods. The first payment due 1 month from now. So that's it. It's at the end of the month, in other words. So that would be an ordinary annuity. Okay, and now here we want to know what rate of interest would you be paying. So if we did a timeline, we would have the $528.77 as our present value. That's how much we owe right now today. If we wanted to pay it off today, that's how much we'd have to pay. Then our rents is $50, okay, and our number of periods is 12. And the I is our question mark. Now, since we have the PV, okay, and we know it's an ordinary annuity, we're going to use PV equals R times table 4, okay, which is the $528.77 equals $50 times the table 4. Okay, so then I need to divide each side. So I need to divide each side by 50 because I want to get table 4 by itself. If I divide R, which is 50 by 50, that wipes that out. Then I'll have to divide the PV by 50. So the 528.77 divided by 50. Okay, and you will get then 10.57534. Okay, so then we're going to go to table 4 and we're going to see, we're going to go across on the 12 period. We're going to go across until we find a number that's somewhat close to 10.57534. And then we'll go up to the top to see what percentage of interest that is. So if we did that, we would see it's in the 2% column. Okay, now this is 2% per month. There's 12 monthly periods at 2% per month. Now, since we put interest in terms of an annual rate, not a monthly rate, we have to take the 2%, multiply it by 12 months. And so our actual rate that we're paying for that MasterCard is 24% a year. Okay, here we have calculating out the rents. Okay, Norm and Jackie Remmers have saved $36,000 to finance their daughter Donna's college education. They deposit the money in Bloomington Savings and Loan, where it earns 4% interest compounded semi-annually twice a year. What equal amounts can their daughter withdraw at the end of every 6 months during her 4 college years without exhausting the fund? Okay, so we have a PV is 36,000. That's how much they're putting in today. We have an I, which is 4%. We have an N, which is 4 college years. Okay, and we need the R, so the R is the question mark. Now, because we are compounding semi-annually, we're going to have to change the I and the N. So the I is 4%. I got to divide by twice a year, which means I'm going to deal with 2%. The N is 4 years, but I got to multiply by twice a year, so that will be 8. Okay, so we're going to use 2% with 8 periods when we look up table 4. Okay, so down here in the red, okay, here's our formula, PV equals R times table 4. We put in our numbers. Our PV is 36,000 equals R, our unknown. We looked up in table 4 for the 2% and the 8 periods. We get 7.32548. Okay, now I need to divide each side of the equation by the 7.32548 so that the R is by itself. So the 36,000 divided by the 7.32548 is 49.14 and 35 cents. That's our R. Okay, so every 6 months, their daughter can take out $4,914 roughly, and then at the end of the 4th year, she'll take out the final $49.14. Here are some concepts in real life. Here is where time value is happening in real life. This is on the PowerPoint, which is on D2L. And so you can take a look at these real life situations. Here's a situation with the state of Wisconsin. And here is a situation looking at what if you were to put money in $1,000 a year. Okay, if you started at age 25, how much would you have by the time you're 65? So 40 years later, okay, you'd have almost 160,000. But if you wait even 5 years and you start putting in money when you're 30, oops, you're not even going to have 120,000. Okay? So you're going to have 40,000 less just by waiting 5 years difference. Okay? So the earlier you start, save